Hey everyone, welcome to this explainer for the Info Engineer channel. Stepping in today as your senior concrete technologist, we are going to diagnose and treat two of the absolute most notorious fresh concrete failures you're ever going to encounter out on site: segregation and bleeding. Look, if you spent any time at all managing a pour, you already know the nightmare of watching a mix just fall apart right in front of you. And we all know these aren't just aesthetic issues, right? They are fundamental structural breakdowns in your material's integrity. We've got a tight agenda today. We'll cover the core concrete separation problem, diagnose the root causes, walk through some highly practical prevention strategies, and wrap up with the structural impact and durability. Starting off with Section 1, the concrete separation problem. To actually solve this, we got to get our definitions straight. Segregation is when the constituent materials of your concrete, the coarse aggregate, the sand, the cement paste, literally pull apart. The heavy solids just physically separate. Now, bleeding is a very specific type of segregation. It's strictly the upward migration of water to the surface of your freshly placed concrete, and it's completely driven by the settling of those heavier solid particles. The fundamental physics driving all of this is a really stark disparity in specific gravity. Your aggregates are usually sitting around a specific gravity of 2.6 to 2.7 grams per cubic centimeter, but your cement is much heavier, usually between 3.1 and 3.6, and water, well, water's the lightest at just 1.0. Because of this massive difference, gravity naturally induces settling. The heavier particles aggressively want to sink to the bottom, and that lightest material, the water, wants to rise right to the top.
Let's move into Section 2, diagnosing the root causes. Why does this actually happen?
You know, a lot of times segregation starts before the concrete is even mixed. Incorrect stockpiling methods are a huge culprit. If you're dropping aggregate from a really high conveyor belt without using a rock ladder, or if you're building piles radially, those larger rocks inevitably just roll right down the sides of the pile. Bam! You've got segregation in your aggregate fractions before a single drop of water is even added. Plus, if you don't protect those piles, the wind will just blow your finer particles right away. And it doesn't stop there. Over at the batching plant, the actual arrangement of your bins and weigh-batchers plays a massive role. If materials get dumped into the storage bin off-center, or if the bins have long slopes because they're grouped poorly, you impair the uniformity right from the get-go. A poor bin shape literally feeds a segregated aggregate stream straight into your mixer. But okay, let's say your batching is absolutely flawless. Once that concrete hits the site, we routinely introduce handling errors that just severely exacerbate both bleeding and segregation. The absolute #1 culprit? An elevated water-cement ratio. Beyond that, dropping concrete from heights greater than 1.5 meters forces those heavy aggregates to violently separate upon impact. And don't even get me started on excessive needle vibration. We've all seen tired crews just leave a vibrator running in one spot. All that does is shake the rocks to the bottom and force the watery paste to the surface. Oh, and transporting concrete over super long distances without proper agitation, that lets those specific gravity differences wreak absolute havoc in the back of the drum. All right, Section 3, prevention and mitigation strategies, actionable methods for the site. The million-dollar question for us technologists, especially when we're designing modern self-compacting mixes, is this: how do we make a mix highly cohesive without completely killing the flow? We have to prevent it from separating, but we still need it workable and fluid enough to actually place. If we just make it insanely stiff, we're never getting it around congested rebar. Well, the answer usually comes down to chemical admixtures, specifically viscosity-modifying agents, or VMAs. We're talking biopolymers here, things like gums, alginates, or cellulose. They act as thickeners. Their main job is to boost the water retention capacity of the cement paste, locking that water inside so it doesn't bleed out, while thickening the paste enough so the heavy aggregate physically can't sink. Think of it exactly like making a pot of soup. If your broth is too thin, all your heavy vegetables sink straight to the bottom and you're left with watery broth at the top. VMAs are like the corn flour you stir into that soup. They're essentially long-chain polysaccharides. When the concrete is just sitting there at rest, these chains intertwine to create a viscous gel that traps the water and suspends the rock. But here's the brilliant part. When you apply shear force, like when you pump it or vibrate it, those chains straighten right out and the concrete flows beautifully. It's called shear thinning behavior, and it is a total lifesaver on site. But VMAs aren't our only tool. Air entraining agents are also fantastic here. Now, usually we think of air entrainment purely for freestall resistance, but it's an incredible trick for reducing bleeding. These agents pump billions of microscopic, non-coalescing aerosols into the mix. Those tiny bubbles act exactly like flexible ball bearings. They completely alter the plastic properties of the fresh concrete, vastly improving your workability while drastically cutting down on bleeding, segregation, and latents. Chemistry aside, our placement procedures have to be spot on. When placing out in the field, follow these exact rules. Number 1, always use drop chutes, tremies, or boom placers if you're pouring from higher than 1.5 meters. You have to prevent that violent impact. Number 2, limit your horizontal lift depths to a maximum of 12 inches, or about 300 millimeters. Shallow lifts allow for proper integration. And number 3, strictly control your internal vibration. Your goal is to consolidate and get the entrapped air out without over-manipulating the mix and tearing the paste away from the aggregate.
Finally, Section 4, Structural Impact and Durability. When you let a mix separate, it kicks off an absolute cascade of long-term structural failures. As that bleeding water carries cement to the top, it forms a super weak, dusty layer we call latents that totally ruins the wearing capacity of your slab and delays your finishers. Worse, as the water pushes upward, it carves out continuous, permanent capillary channels. This permanently spikes the permeability of your hardened concrete, practically inviting water and chlorides right in, which leads directly to rebar corrosion. Plus, that excess water pooling under your rebar physically breaks the critical bond between the steel and the cement paste. And then there's the most visible consequence, honeycombing. There is absolutely nothing worse on site than stripping the formwork and finding a honeycomb staring back at you. It's a severe structural defect where the paste has washed away, leaving the coarse aggregate completely exposed with massive voids. Because the paste and sand are gone, the structural integrity of that entire zone is shot. Tap it with a hammer and it sounds completely hollow. Fixing it means incredibly expensive, time-consuming post-pour repairs, like structural patching or grouting, just to restore the element's basic load-bearing capacity. The American Concrete Institute, specifically ACI 304R00, hits the nail right on the head with this quote. The more a form is filled with the right combination of solids and the less it is filled with water, the better the resulting concrete will be. It sounds almost too simple, doesn't it? But minimizing that excess water and engineering a perfectly cohesive, optimally graded blend of solids is literally the ultimate key to preventing these defects and ensuring your structures actually last for decades. So I want to leave you with this thought to take back to your next pour. Are your current quality control procedures genuinely preventing the hidden, long-term costs of concrete separation? Make sure you're actually placing engineering-grade concrete, not just dumping a separated mess into the forms. Thanks for joining me on this explainer. Stay safe and stay focused out there on site.